Okay, well, welcome everyone. Thanks for coming to the second UTIG seminar of the semester. And today I'm really delighted to introduce Xinting Yu, who is an assistant professor at the University of Texas at San Antonio in the physics and astronomy department. And she joins us after doing her PhD at Johns Hopkins University in planetary science and her bachelor's in space physics at the University of Science and Technology of China. And then prior to that position in San Antonio, she also did a postdoc at the University of California in Santa Cruz, where she was a 51 Pegasi B postdoctoral scholar. And all of this work has really emphasized her interest in planetary materials, and she's been developing this really awesome database using experimental work, which then she couples into theoretical and numerical modeling work to understand the surface and atmospheric and those coupling processes, both within our solar system with a special focus on Titan that we'll hear about today, but also with exoplanets. So this great work has been recognized with the NASA Early Career Award. And she's also maybe somewhat familiar from you all through the Texas Area Planetary Science meeting that was held maybe a month or a few weeks ago, which
feels like forever ago because I've been teaching this semester.
Yeah, so she was able to get funding to organize that inaugural meeting through the Heising-Simons Foundation. So we're really delighted to have her today. And with that, I'll pass it on. Thanks.
Thank you so much for the nice introduction. So nice to meet you, everybody. I've never actually been to any of the UT campus, so it's really, I guess, like for me, it's like this is the first UT Austin campus ever hit, and it's like super nice and everything. But today I'm gonna be talking to you about this very mysterious feature called the Magic Islands on Titan, how we use some of the laboratory data and theoretical models to understand these features, kind of decipher their mysterious nature. Okay, so this work also involves some of the undergrad students I have in the past as well. All right, let's see if this works. Okay, so I kind of start this story as a story kind of thing, like, and I want to have you go all the way back to like 2019. So I don't know if anybody has been to like this meeting. So this is a EPSC DPS joint meeting in 2019. It's in Geneva, so it's very nice. Okay, like town for sure. Has anybody been there? Yes. Oh, okay. Lots of you have been there. Okay, yeah. But if you remember, it's a nice town, but not so much the convention center where we're having the conference. So if you remember, these are kind of the conference room, right? So imagine like a, there's not so much AC there, so like it's kind of hot. Imagine like an afternoon, like maybe 2 p.m. Okay. So we're sitting in the Titan session, okay? And then, so there's a scientist, his name's Daniel Codier. He's giving a talk, okay? And he gave a talk first, and then which I'll talk about the next slide. And then he had no idea what I'm gonna talk about right after that. So in 2019, I just finished my PhD. I was just about to start my postdoc. And I was kind of like, I would say, having a very contradictory theory with this very senior scientist. Okay, so Daniel gave a really cool talk. And it's about Titan's lakes, okay? So I would say one of the mysterious things about Titan is that, of its lakes is that we actually think very smooth. It's very, very smooth. So what that means is actually there's work done by some UTIG researchers in the past, but all of the radar observations we have on the lakes show that the lakes are super smooth and wave amplitudes at most just a few millimeters. So we're talking about something like tiny, okay? And you guys been like flying probably over, airplanes, and you probably can see some of the lakes on Earth, and they're definitely not as smooth, right? So Daniel gave this talk, and his basic idea, I think is pretty cool when I saw it, was like, if you can have a layer of like floating material on the surface, and in this case, he thinks the floating material can be lifted up by a capillary force from the liquid, okay? You can then, it's kind of like how you have like an oil leak on the Mexican Gulf. We know like kind of oil can dampen the waves, the amplitude of the waves. But like, if you have a floating layer of aerosols that's falling from the atmosphere, maybe you can also dampen the waves. And maybe that's why we don't see much waves on Titan lakes and seas. So that's the talk he was giving. And he did not know what I'm talking about next, which I said, there won't be a floating layer of aerosols on Titan's lakes and seas at all. because I think there's just not going to be, the capillary force is going to be 0 because the liquid is so wetting. So it's not providing that extra push to the particle. So that's what I was saying. All right, so what has happened before that? So I want to kind of back it up a little bit. Why did I give this very controversial talk right after his talk? Right. So back a little bit. So, my PhD, my PhD is completely on like sediment transport on Titan. So I study dunes on Titan because, and it's really important because on Titan, the materials that are making up the dunes are not like the silicate or the quartz sand that we see on Earth, but instead they're organic material that are falling from the atmosphere, and they form kind of the dune material on Titan, right? And during my PhD, I was really trying to understand how does the material property of the dune particles on Titan kind of makes the dune forming process, differently, or like maybe similarly compared to the dune forming processes on Earth. And during my PhD, I measured these material property of the organic analog on Titan. And basically I found, well, they behave actually quite differently than the Earth's material through all these properties. So I did, for example, some cohesion measurements, the surface property, I found the Titan sand is much stickier. I did some electrical property measurement, basically figuring out if when the sand are being transported to form the dunes, when you rub it, do they like kind of produce like charges that make things more complicated? But apparently they barely produce any charges, which is very different compared to quartz sand. And also they're mechanically much weaker, so that means they don't last as long when you transport them. They will be very easily abraded to very small particles. And it's actually crazily hard to move very small dust-like particles. But anyways, I did this whole thesis on like dunes, and my thesis title is kind of like sediment transport and dune formation on Titan. Everything was actually quite great after I finished my thesis. So that was June 2019. Okay, June like 1st, something like that. And then like 27 days later, NASA selected this mission called the Dragonfly mission to go back to Titan again. And you know where it's gonna land? It's gonna land right in the middle of the dunes, where like my PhD is at, which is pretty cool. So it can really enable all the capacities. I was doing all the measurements of the dune material, the physical properties, but the Dragonfly actually can do it also. So we can really validate the stuff, the organic analog which we're using in the lab, whether they're similar to the actual materials on Titan. And of course, Dragonfly is actually astrobiology related mission. So we're trying to see how far has prebiotic chemistry has gone on the surface of Titan. But anyway, this is all great. And then I happened to encounter Daniel's paper actually, just again, like maybe within another month after Dragonfly selected. Okay, so someone sent me this paper, they're like, you should read it. I'm like, this is totally a cool idea. If you can have a floating layer of aerosols to dampen the waves, to explain why the waves are so smooth, that's a great idea. But then I actually read the paper a little bit more. Okay, here's what I read. So apparently, when Daniel wrote the paper, he's saying none of the experimental measurement exists. For example, he said, okay, so something like a more specific conclusion cannot be drawn because the mechanical properties of the films, which is the organic materials, never measured, okay? And my paper was published in 2018. And then he also said, oh, like, the contact angle measurements have not been measured either. I'm like, I did that in 2017. So, that's why, when we describe the science we do, it's like, a villain versus like kind of stories like, the villains are the series that don't use laboratory data when they exist. I was like, okay. I was like, again, like a very, new postdoc, just finished my PhD. I was like, I could do better than this because I actually have laboratory data that can actually, validate or like maybe disvalidate this theory. So that kind of started my whole journey of like understanding whether things can float on Titan or not. And it's a very long journey because I just submitted my paper like a few weeks ago. So it's been like 4 years later. Well, we have a few like in between, but this is my, I guess, final paper on the floating stuff that's just submitted a few years ago. And I'm gonna talk to you today about this journey from 2019 to 2023, what I did in between, okay? And what did I figure out? And how did that lead to me to understand the magic islands on Titan, okay? All right, just a little bit more like background material, just in case you don't know Titan super well. There are so many cool things about Titan. One of the cool things is Titan actually is the only other body in the solar system other than Earth with standing liquids on its surface, okay? But the liquid on Titan surface is very different. And the main reason is because of temperature, okay? So on Earth, we know water can exist in like different phases, like a solid, as a liquid, as a gas, because the Earth's temperature is actually pretty close to the triple point of water, okay? On Titan, the temperature is so much colder that water just stays frozen like all the time, okay? But Titan's temperature is actually very, I would say, great for methane. So it's actually very close to the triple point of methane, which is 90 Kelvin versus like 94 here. So that means on Titan, methane can easily transform between like liquid and gas, and actually solid is hard for some different reason, but there's actually an active methanological, if there's a word, like a methane cycle on Titan. And that's why we get to see these like really nice lakes, but they're not made of water, but made of liquid methane, ethane, and also some dissolved nitrogen from the atmosphere, okay? So this is kind of the background information for you. And we get to learn a lot about the lakes actually through the Cassini-Huygens mission that spent like 13 years there, from like 2004 to like 2017. And I would say after the Cassini mission, there still remains to be two like big mysteries about the lakes. And the first one is what we just talked about. Why are the lakes so smooth? Okay, what's happening? Why are the waves so tiny? And the second one, which I think is really cool, is the magic islands. So what are the magic islands? Okay, so here is just kind of a paper showing you, this is kind of the lake. You can see a lake, and there are some like little islands over here. I think I'm pointing at the wrong direction, but let's see. Well, I'll just point, but in the green circle is like kind of some islands over there. Okay, so you look at that area that in the green circle, and then maybe a few years later, something appeared, and they made sure it's not an artifact of the radar data whatsoever. Okay, this is the first time they've seen it, and then they actually have seen it appeared, disappeared, and reappeared, and then disappeared again. Okay, and we have no idea what it is. And there are like 10 hypotheses that we started with, but now there are only a few left. Okay, so I would say at like now these are kind of the hypotheses that are left to be validated, but there are still like a few left. In terms of why the lake's so smooth, there are like two. Either there's just no wind, so there's just lack of waves, so because there's no wind, or maybe it's the Daniel's idea about the floating solids. Okay, and for the magic islands, well, they started with like 10 hypotheses. There are like about 4 left right now, so it could be, there may be some, even though in general there's no waves, maybe there are some occasional waves that could generate these features, and the waves look like just like the same as floating solids in radar, unfortunately. And it could be floating solids, or it could be suspended solids, but it's gonna be suspended in the very top part of the lake. Okay, so it means radar can see it, so it can't be like over the radar's wavelengths. And then it could be maybe bubbles that's bubbling from the inside of the lakes as well. So these are the 4 kind of for the magic islands. But I don't know if you notice, there are 2 things that can actually simultaneously explain both these serious features we're seeing. We can use waves to explain both things we see. When there's, well, in general, we think there's not so much wave, so the lakes is flat. And whenever we have an occasional wave, we see the magic island. Okay, and the floating solid hypothesis also work. So if you have a floating layer of stuff that's like kind of small particles, that would explain why the lakes are so smooth. And while if you have some larger chunks of floating solids, you will see magic islands. Okay, and in this talk, I'm going to explore whether floating solids can contribute to making up the magic islands on Titan. Okay, well, how do you float stuff on like a lake to begin with? It's actually not a hard problem. There are only like 2 forces that comes into play with it. Okay, so if you have a particle falling into like a lake material, you could have this capillary force. So the capillary force is either 0 or it's above 0, but you always try to either not do anything or push the particle up, okay, through this capillary like surface tension effect. And the other force is buoyancy. And it's basically a density comparison between the particle and the liquid, okay? And basically, if the particle is less dense than liquid, you're going to have a buoyancy flow that goes up. But if the particle is denser than the liquid, you're going to have buoyancy force pointing down. Okay, so there are two scenarios to make things float. The easiest way is if your particle is less dense, both forces are kind of pointing. So the capillary force is either 0 or bigger than 0. So both forces will kind of point up. That means the particle is definitely going to float. That's the easiest way that's going to make it happen. The second way is a little bit complicated. Well, when your buoyancy force is less than 0, you're going to have two forces, and you need to kind of balance the two forces to make it happen. And because we know the capillary force is related to this parameter called the contact angle, so basically how wetting the liquid it is to the particle, we can then figure out whether the capillary force is big enough to make the particle float. And that's what Daniel was suggesting. You know, he's saying if we have a big contact angle, we can make things float through capillary force when it's big enough to kind of counteract gravity. Well, if we have a too small, like a contact angle, it doesn't happen. Well, it turns out that contact angle is not that easy to get. And the reason being, it's actually very dependent on what material you have, okay? So here I'm showing you kind of the standard like Young's-Dupré equation governing what, if you have a liquid and a solid material, you put the liquid on the solid, what kind of contact angle you would be forming on the liquid, okay, on the solid, okay? And apparently it depends really on the surface property of the material, both the liquid and the solid, okay? So that means we need data to do this. I would say like the real surface properties of both liquid and solid material to be able to calculate what kind of contact angle can exist. All right. Now let's actually talk about what kind of material can actually form on Titan's lakes. Okay, so we want to know that to be able to assess whether things can float or not. Well, this is something like I'm really interested in because I love chemistry. I don't know about you guys, but in Titan's atmosphere, the second thing that makes Titan great is Titan is actually the only moon in the solar system with a substantial atmosphere. And the atmosphere is actually amazingly similar to Earth because it's mostly nitrogen. So we have about 98% of nitrogen and about like 2 to 5% of methane, depending on where you look. And because it's exposing like an energetic environment, you have the solar UV photons hitting the atmosphere all the time. You also have some energetic particles from Saturn's magnetosphere hitting the atmosphere all the time. You initiate this amazing chemistry that makes organic molecules. And methane is actually really, really good at making organic molecules. And I'm just showing you like a it's not exhaustive list of like stuff that we're seeing in the gas phase for the simple organics. There are at least like 18 of them so far, and I'm pretty sure we're going to detect more in the future. Well, this chemistry doesn't just end there because these simple stuff can further react, polymerize, coagulate, and eventually they make these really complex materials that are refractory, which means they're solid. Okay, so they don't go through phase transition. They're just so big in molecular weight, and they're already like a solid material. And we think these are actually the particles that makes up Titan's thick haze layers. And that's why whenever you see an image of Titan, it looks like a giant orange ball because we're not able to see its surface in visible light. All we're seeing is this thick haze layers. That's all kind of orangish. Okay. But anyways, we think the complex organic makeup the main material that kind of settled down on Titan's surface. Okay. All right. So basically the question now is, how does the complex organics interact with the lakes? Okay. And there are three things that could happen when they enter the lake. They could either dissolve into the lakes, or maybe they could float, which would make the lake wave dampen thing happening. And then they could also sink into the lake, just become lake bed sediment. Okay. Well, to study this, to date, actually, I think you all know this, we do not have a sample from Titan. So how do we even study this complex organic material on Titan? Well, we're laboratory material scientists, so we're smart because we can actually recreate a planet in a laboratory condition, okay? And what we do is we actually can have some gas mixture, in a chamber that's mimicking like Titan's atmosphere condition. And by exposing this gas mixture to like a similar energy source that Titan's atmosphere is getting, for example, we can use something like a UV lamp to simulate UV photons from the sun. And we can use something else called the cold plasma to simulate those energetic particles, okay? And then we let this reaction goes for like a few days, we would make this final material that's kind of just the right color compared to Titan, I would say, right? The orangish color. And we actually, this material was actually invented, I would say, by Carl Sagan, his colleague Bishop Carey, and they decided to name this material Soling, which means muddy in Greek. And if you deal with this material in the lab, you'll know what I'm talking about, basically. Okay, all right, so this is the material we have. And I'm not going to talk about, okay, but basically we have done experiments that shows that these materials, they don't really dissolve in these hydrocarbon liquids. So we don't think their fate is dissolving to liquids. So now the question is whether they float or sink, all right? And I think I'm going to talk about some detours that I did. And, you know, that's why it took 4 years to have this paper out. Okay, so I've been like generating haze. During my PhD, I was in like a haze production library for Titan. But during my postdoc, I get to talk to more people who are making Titan hazes. I'm like, okay, everybody's making this haze, but who makes the real haze on Titan? I was like, why? Like, you know, what? So here I'm just showing like what I'm puzzling about. So here are kind of the 3 labs I get to talk to their PIs about. So these are all like haze, Titan haze activity. They're actually producing Titan hazes. But as you can see, if you look at the kind of main experimental condition that goes into making the hazes, you'll notice there are actually many ways, seems like you can make Titan hazes. For example, some of the experimental condition, like this gas exposure time, actually varies by orders of magnitude, right? When they're producing the hazes. So actually, I wrote a grant to do this big comparison study of different hazes produced in the lab, and the only reason is trying to figure out, with comparison to Cassidy and Huygens data, which haze is better, or what kind of experimental condition makes hazes that mimics Titan the best, okay? But this is a detour I did to measure the property in the end. But kind of how we do this is basically we have all these different labs makes different hazes, but that's kind of the only difference in our comparison study. And they will be actually all transported through a standardized approach, which means they don't really touch air all the time. And the reason we don't want the material to touch air is because it's made only by nitrogen and methane. We never had oxygen in the gas mixture, okay? So that means we do not want Earth's oxygen and water vapor to kind of contaminate the material. These are kind of some of the vessels we developed in the lab with my student to transport them. And we also store them in like dry nitrogen glove boxes. So there's, again, they don't touch air. And also measure them in dry nitrogen. So this is like a setup I built, you know, with some Home Depot gears during my postdoc, maybe like $300, and they work great. We have 2 papers out already with this setup. But this is kind of the idea we had. And during my postdoc, my undergrad student Jelling, we did a first pilot study, and we measured 4 samples generated from like these 3 laboratories. I mean, there's many things we found, but I would say 3 main things we found from this pilot study is the first thing, you know, even though all these labs seems to be using very different conditions to make solings, it seems like there's some experimental condition that matters more than the other. So it seems like if you use the same energy source, you somehow end up making similar material. So the surface energy is kind of what dictates the cohesiveness of the material. We can also kind of separate it into 2 components, the dispersive component and the polar component. And that gives you some kind of idea of the bulk chemistry of the material. So if the material has like a large polar component, you think it has like lots of polar structure inside. But in any sense, it seems like if we use the same energy source, you produce similar material. And the second thing we found, or we get to the communities, like we now can provide a range of numbers for people to use, rather than like 1 number with standard deviation from like 1 lab. Okay, so this is what I'm using in my theoretical work. And lastly, you know, you're like, oh my God, all these solings are different. What do we do? But it turns out that they do have a common property. They do share a common property, which all of these samples seems to have a high dispersive component, which kind of, I would say, given that all these things are produced so differently, but they have the same property in the end, maybe that's a property we should be more confidently, to use in our theoretical works. But anyways, we use these data that we generate from our own lab work to figure out whether things will float or sink, okay? And basically what we found is no matter which soling property we use, their surface property, the contact angle we get is always 0. Okay, so the liquid just so wetting, because methane is a very wetting liquid. It's just gonna wet whatever solvent you make in the lab. Okay, so that means the only way to make solvent or like the complex organic float on Titan's lake would be if it's fluffy. And you can't float through capillary force like what Daniel proposed, basically. That's what we found. With our larger deal of doing the comparison study, getting all the properties and coming back to the theoretical work, okay? So that's great. We got 2 papers out, the comparison study and the first pilot study I did, 2020 and 2022. And then we're like, that's not the end of it. And the reason being, there are actually more materials from Titan's atmosphere falling to the surface, not just the complex organics, okay? So you guys remember, I showed you all these things. So these are the 18 molecules that have been detected in the atmosphere, okay? They're in the gas phase when we form them. But the great thing is, when they're falling towards the surface, because the temperature drops, these things actually can condense, become a liquid or a solid, and then they fall to the surface as liquid or solid. And then we're like, okay, we got to explore whether these materials float or not, because they could be candidate material to make up the magic islands or the floating solids to dampen the lakes, the waves on the lakes, right? And so this study now becomes, well, we are studying first, what happens to the simple organics and the complex organic, and both of them, when they fall toward the surface, whether they dissolve, float, or sink, okay? All right, to be able to do this, and we publish these for the complex organics, and work is mainly exploring the simple organics, okay? All right. So there are lots of molecules, and if you guys remember, the contact angle is material dependent. So that means we need a lot of data to be able to do this work. And this is the second detour we did, which is the material property database that we made. And the paper is just out this year, but it took generations of undergrad students, and like 3 years to make this database to get all the data we need for this theoretical work. For example, to be able to understand whether these organic material, when would they change from the gas phase to the condensed phase, or whether they change to liquid or solid, we need all these thermodynamic properties, like phase change points, saturation vapor pressure, to be able to do that. And we also need their density to figure out, whether they are denser or less dense compared to liquid, right? We also need their surface property to figure out the contact angle. So these are just all the data we collected and something else. But this database is out, and here's a QR code to the website, and the paper is out. So feel free to check it out. And even if you don't do Titan stuff, if you do anything that's like kind of icy body in the solar system, if you encounter, you're going to encounter similar molecules like complex, simple hydrocarbons like ethane, acetylene, and even planet formation people. So feel free to send it to your friends, and maybe they're going to find this database useful. All right. But just want to give maybe a few more highlights of the database. So we're really proud of, we're finally getting a complete set of like saturation vapor pressures, which doesn't really exist in the field. The last paper was published 2009, okay? So basically we have this interactive website. You just kind of stick a temperature, you'll get the saturation vapor pressure at a certain temperature. And the next thing we did, I apologize for showing you this huge table, but I just want to kind of bring your attention to this kind of temperature column that's circled by this big red box. So basically, we're actually providing some directions for the field. So all these temperatures you're seeing, if they're kind of in brackets, that means there's no laboratory measurement. So the relationship is an extrapolation to the existing temperature range. So this basically is like a source of proposal, idea spot. So if you want to measure vapor pressure, you should look at this table and see what's not being measured, what temperature has not been done for some materials, and then go for finding opportunities, okay? All right, but we finally got all the data, and now we're using the data to do the work we want to do, which is whether simple organics, what's the fate of simple organics when they're on the surface, okay? And the first thing we did is, okay, we need to figure out what phase of these simple organics are when they're on the surface, whether are they a solid or a liquid or a gas, because we think only the solid things can make the floating layer, okay? And this is also important actually for dragonfly mission, because dragonfly would want to know what kind of material would they encounter and what phase they are, okay? And to do this, we use a thermophysical data we collect in our database. And we found out, well, most of the organics would actually not condense as a liquid. All of them would condense as a solid in the atmosphere, okay? And then we can use the phase change point to figure out, okay, when these solids land on the surface, do they stay as a solid, or maybe they change phase to a liquid, or maybe to a gas? And this is what we found. We found there are 12 species that are able to stay in the solid phase. There are 4 that are in the liquid phase, and there's 1 that's only in the gas phase, okay? And for our flotation work, we're only gonna use the species that are in the solid phase and check out their interaction with the lake liquid, whether they dissolve, float, or sink. And again, the first thing we look at is dissolution. And it turns out that the solubility of all of these molecules actually pretty low in the lake liquids, which means over geologic times, we think the lakes is probably fully saturated with all these simple organic molecules, okay? And that means any incoming new particles is not gonna dissolve, which means we're gonna explore whether they float or sink again, okay? And just to remind you, this figure that I showed you, how can we make things float on Titan? We have the capillary force that's helping the flotation, and the buoyancy force either helps or not helps, okay? So again, the first way to make things float is, if you have a particle that's less dense than liquid, you could potentially make it float, okay? So that's the first thing we explored, is basically simply comparing the density of all these ices to the lake liquids of Titan, okay? And what we found is everything, of course, they're denser than the lake liquids, because the lake liquid is methane, ethane, nitrogen. They're all like pretty low density material. Well, when you form an ice, maybe it's not gonna be just the ice. Maybe it's gonna have some pore space in the ice, okay? So the next thing we explore is, okay, if we have some level of porosity in these ices, what level of porosity do we need to make things float on Titan? And this is the second plot I'm showing. So we kind of plotted the porosity level that are needed for each ice, okay? Because they look different because of their density. And well, Titan's lake is actually not a single component lake. So we did kind of single component here, like we did this liquid methane, liquid ethane, liquid nitrogen. But it's a ternary mixture of 3 things together. Well, so that's gonna bring you guys the ternary diagrams, which everybody hates, but I'm gonna go for it. But the basic idea is, this ternary diagram, every point kind of is indicating a composition. Okay, like maybe you have 90% methane, 8% of ethane, and 2% of nitrogen, something like that. Each point is kind of like that. And it's not like Titan's lakes. Actually, we do have measured composition of the lake. It's not like the lake is kind of covering up the whole like ternary diagram. Okay, all the possible composition. The lakes actually only occupies this small areas shown in these like diamond boxes. These are the measured composition of the lakes. Okay, on this diagram we showed contour plots, and these contours are showing you the porosity that are needed to make things float on certain compositions, if that makes sense. Okay, and basically what we found is, for some low density ices, you only need, given the lake composition we know, you need the minimum of 25% to make things float, porosity. But if you change to a different ice, it could be as high as 65%, okay? And they're like, okay, is this porosity level possible? Well, the answer is we actually don't know, because we never measured, well, we don't have enough measurement on the porosity of how much porosity these ices can get. But we do know something about, the snow on Earth, we think, which is I would say a good analog to the ice, well, I would also call it snow on Titan. And actually on Earth, the snowfall particles are actually super porous. Their typical porosity is like 50 to 60%, okay? And they can even have porosity as high as like 90%. So if these ices can behave just like the snowfall particles on Titan, we think they could potentially float on the lake liquids. So it's not, that's uncertain, but we think it's probably possible. Well, we then go on and investigate the other way to make things float, which is through the capillary force, okay? Given that most of these material are a little bit denser if there's no pores. And capillary force is basically we use, again, it's related to the contact angle between the lake liquid and the solid. And the larger the contact angle is, you're going to have a larger capillary force. So just going there again. But okay, what kind of contact angle are we talking about? So the first thing we did is we estimated the threshold contact angle that's needed to make things float, to have enough capillary force to balance the buoyancy. Okay. And what we found is if you have very small particles, like aerosol sized particles, about like between 0.1 and 10 microns shown on the x-axis, you only need like just a little bit above 0 contact angle to make the capillary force big enough to counteract gravity, which makes sense because the particles are so small, right? But if you hit much bigger particles, like that are actually, small snowfall size or surface sediment size, you actually need much larger contact angle to make things float. Okay. And now with our surface property data from the database, we can estimate the contact angle that's formed between all the different ices and the liquids on Titan. All right, ready for the result? For methane. So if we assume a pure methane or ethane lakes, as you can see, the contact angles are all 0. Again, these liquids are so wetting, they're just going to go everywhere and they're going to flatten out. They don't form a contact angle that's bigger than 0 degrees. All right. Well, for ethane, though, we do see 2 species that have non-zero contact angles finally. And because, again, the lake is a ternary mixture, I'm showing you a ternary diagram again. I'll try to do my best to explain this, but we have the ternary diagram. So what we're showing here in the color regions is basically wherever the contact angle is not 0, okay, bigger than 0, for the 2 species that have non-zero contact angle with ethane. And these purple and blue kind of diamond boxes are showing you where the measured liquid composition. But basically what you can see is for acetylene, C2H2, it doesn't really, its non-zero contact angle area doesn't have any overlap with the measured lake composition. So we don't think this ice can ever float on Titan's lakes with known composition. But it looks like solid HCN, which is totally not healthy, may have non-zero, may have some like non-zero contact angle areas that do overlap with measured lake composition. So our conclusion is maybe it's able to float on ethane-rich lakes, okay? But the thing is, there's actually only one lake with that composition that's kind of overlapping with that non-zero contact area, and it's a lake in the South Pole. All the ones we've seen are mostly, well, most of the lakes on Titan in the North Pole, and this is where we see all the magic islands and stuff like that. There's no overlap at all. So we think it's very likely the capillary force is just not responsible for any floating stuff on Titan, if there's any. Okay. All right. That's kind of it, but not really. I do have some time. Yeah, we have 10 more minutes. But okay, so we made this material, like this summary figure showing you kind of the fate of all the simple organics and complex organic in our paper. But this is not it. This is because there's a timing issue. Okay, so if you see these magic islands, it's got to be the right time scale. You can't float for too long or too short. What does that mean? Well, so for example, here I'm showing you like a magic island people have seen like on another lake called Krakenberry. So that's the largest lake on Titan. And basically 2 hours after the observation of the magic island, they also take another data set, which is through the visual and infrared mapping spectrometer on Titan. And they kind of see this red feature on there, which is probably also the lake, depending on how much you trust this data. But anyways, we think based on all the observations we have, these features have to last. If you float on it, either from a couple hours, it can't be just seconds. It has to be longer than that, a couple hours or a few weeks, but not so long. Okay, it can't be like too long or too short. So this timing is important. So now if we go back to evaluate whether, for capillary force, for example, for the capillary force induced flotation, once you hit that, you're not gonna stop floating. You're gonna float there forever, pretty much, okay? So this is just floating for too long, I would say, if that makes sense. Well, how about like the porosity? If you have enough porosity, how about that flotation time scale? Well, that time scale depends on, because the particles are porous, it depends on how the liquid is kind of, how long will it take the liquid to fill all the pores, making the particles like dense enough to sink, right? So we actually calculated that time scale, okay? Through this infiltration theory we have. And basically what we found is, in order to hit this 1 day, which is in the purple line, you have to have very large particles. But for anything that's like kind of regular, I would say like reasonable sediment size, your flotation time scale is tiny, like maybe a few seconds in the maximum, okay? So like basically we're like, okay, neither capillary force or porosity-induced flotation would work, okay? And I was about to finish a paper and submit it, until one day I was kind of maybe reading the news or browsing the internet, and I saw this thing. I was like, what the heck? Have you guys heard of this? Pumice rafts, okay? So pumice rafts, I mean, if you guys know pumice are these like very porous volcanic rocks, and they're kind of erupted by volcanoes. And actually, you dump a bunch of things also on the ocean. And these pumice actually can stay floated for like weeks and months, and some of them even float for like months and for years. And they kind of actually move from continents to continents, and they form these like kind of island feature here. And I was like, it's not making any sense to me, because the pumice should not float for so long. And the reason being three. First, it's a rock, so its material density is larger than the liquid water, right? And the second, water is actually very wetting to the pumice, so it should fill all the pores quickly. And then we know it only have like open pores, so every pore should be filled quickly. So it doesn't make any sense why this thing would float for so long. Okay. Well, I actually did some experiments. I was like, what the heck? And then I'm gonna show you guys today. So I got some pumice. Okay, let's see if it works. So I got a beaker here. Okay. Let's actually drop some pumice in this and see if any of them is gonna float. Okay, like, does anybody want to do this while I keep talking? Just like drop these guys to the liquid. Okay, for example, this guy, do you guys see that? Yeah, yeah. Okay. This guy, so like I did this experiment, for example, I saw like 6 particles floating, okay? And 2 days later, this is like apparently my kitchen countertop experiment. 2 days later, I have like 3 left, okay? Oh, do you see that one synced, right? Okay, all right, but just like it seems like just a few of them would stay like longer, but a few more days later, we still have like 3 left. Okay, so they did float many. I was like, I'm an experimentalist. I have to try this before like I really believe it, but it actually did work. But I'm not gonna drop everything there, but you guys can kind of see it does stay floated. Most of the time, actually, you can see like bubbles coming up. So that means actually the liquid is going inside the pores, right? So that's what's happening. But it was like, but still, like, why do they float for so long? Well, it's like, like you think people understand this phenomenon, but we don't until 2017. Someone did some measurement using this technique called X-ray microtomography. They kind of image, the distribution of gas and like rock and liquid when they do this kind of infiltration experiments. And what they found is there are tons of air bubbles in the ones that stay floated inside, okay? And why is that even happening? So apparently this is dictated by 2 forces again. So now the viscous force is playing a role, and the capillary force. So the basic point is, if you have a large viscous force, if you have a pore you are trying to go in, the liquid is just gonna all flood in like this, okay? But when you have a large capillary force, what happens is the liquid is not gonna flood it in, right into the pores. Instead, it's gonna go around the kind of edges, okay? It's gonna fill all the edges. In the end, what happens is like you can see these bubbles being trapped in these pores, okay? But it is like the infiltration theory still works. It just only fills the edges instead. But now the time scale actually controls the flotation. Well, for all the pores to be 100% filled is how long does it take the gas inside these bubbles with trapped liquid go out, okay? That's the time scale that controls that. Well, this doesn't happen all the time, because only when capillary force dominates the scenario, you would get this kind of gas trapping. So the first thing we did is we look at what we calculate this capillary number, which dictates whether gas trapping would happen. So basically, when the capillary number is less than 10 to the minus 5, we think it might lead to gas trapping. Okay. And what we found is, well, given all the possible Titan parameters, you have to have pretty big sediment to make gas trapping happen, but not that big, but just like a few millimeters in size. Okay. And then we plotted kind of, if we assume gas trapping, like the diffusion timescale dominates the timescale of the flotation, how long would it take for things to float? And they kind of increase the timescale by orders of magnitude compared to the infiltration theory. And we do actually can have particles float for like days and months, not so much years, I would say. So like, the right kind of timescale. So this is like, literally I discovered this and I have to rewrite the paper and everything. But we think this is actually possible now with porosity-induced flotation, but only for larger particles that are millimeter size. And that tells us something about the origin of these kind of magic islands, because people, again, have proposed a different mechanism to make these magic island, like the material. For example, they could be delivered by a fluvial activity or like aeolian activity, or maybe just raining down from the atmosphere. Or maybe it's through some events like mass wasting, so like huge amount of material dumping, or glacier carving, stuff like that. But we know that these processes, they only produce smaller particles. So we don't think these processes are like kind of contributing to the magic island phenomena. It's probably these guys that are really violently, dumping a lot of material that are probably larger particle size to the lakes that's causing the flotation. If this is what's happening to explain the magic islands. And I think that's pretty much it, but I want to end the story because you think me and Daniel is doing very bad terms, but actually now follows me on Twitter. And like I think he comments on my posts sometimes. I want to spend maybe like a minute talking about my lab and advertise for it. But okay, so this is what I'm building as a new assistant professor at UT San Antonio. I started in January. What I do is like planetary material characterization, but these are kind of the materials I do and all the properties I do. And these are the instruments I'm getting. So I'm getting instruments, a nanoindenture to measure all the mechanical properties, all the ellipsometry. Oh my God, I can't pronounce like this word today. Ellipsometry to get optical properties, and the atomic force microscopy to measure cohesion and other things. And I would say the unique part of PM Chef is all the instruments going to be housed in dry nitrogen glove boxes. And we actually did a study to show you why it matters. So my student, well, I have two Eric, which are both amazing, but we actually did a measurement comparing a pristine sample that's never been exposed to air, a Titan haze sample, and a sample that's been exposed to air for like maybe like a few weeks. And we found everything changed. So the surface energy changed, the chemistry definitely changed because the dispersive component and the polar component all changed. So we tried it on different substrates, but the substrate effect is nothing. It's just whether the samples are exposed to the atmosphere. And so far, we have not been doing measurements. Most of the measurements in the controlled environment. So that's what I think is needed, not only for the Titan haze sample we make, but also for other pristine material that are coming from outside. So in our lab, we want to do not only these the Titan hazes, we want to do other things. We want to spot future missions that are return sample to us. We also make some new materials. I also do some other things as well. And we want to eventually apply all these data to understand processes inside and outside the solar system. And I think that's it. That's it. I'm done. I feel like I want to drop more of these until one stays floated. But I will take any questions.
All right. Thanks very much.
Not this guy. Okay. Oh.
You. Oh, thanks. That's a really interesting talk. And you answered a lot of my really good explanations. You answered a lot of the questions I had along the way.
Okay.
But one that's left is a little bit related to the scale of the kind of stuff that has to be floating, both for the question of if it's stabilizing the lakes against waves and also for explaining the magic islands. Now, you talked about it at the end, sort of you need large scale stuff calving off or whatever to be able to explain that they're floating around for so long. But what about constraints from maybe from the observation side of the radar? I don't know, maybe that's going outside your area, but are there constraints on the scale of the stuff, like and then maybe the texture of it, and then also on the side of those stuff that's got to be stabilizing the waves?
That's a great question. So I actually do talk to some of the people who do like radar observations on Titan and also the infrared observations. So for radar, the matching line, they found it has to be like something like 10 meters of material like dumped there to be able to make that big feature, something like that. But so if it's coming from like the island next to it, it's not gonna change the morphology of the island. So it could be possible that's just coming from the island that's next to it. The floating layer of solids on the surface is actually pretty hard for the observation people. Like the radar people can't do what, because the wavelength is like 2.2 centimeters, can't really figure out the surface stuff. I think there might, well, and also like radar is kind of, the data is degenerate, so you can have like multiple interpretations. That's my understanding. So you could explain things with multiple ways. And I do think there's a paper talking about, it could either be like a floating solid or something else that could explain the radar observations.
Right. Oh, sorry. I should have clarified it.
Oh,
Less
okay.
about the observations for that one. That's more about like what like the theory is about how big a set of particles you need to stabilize the waves.
But to stabilize the waves, I think like aerosol size, like like if tens of microns. Okay, then yeah, if that answers the question. Yeah, small particles.
Hello, thank you. That was a really great talk, and I loved the little floating rocks up there.
But not not floating yet.
So this is a dumb question. Why can the Magic Islands not be explained by just like a change in level of the lake? Like if there's a big pointy peninsula or something that appears when the lake level is low and hides when it's high.
Let me think. I think they did rule that out in the first paper they did. Like, they rule out something like volcanic, like something like forming the Hawaii like island chain. Something. I think it's the sea level is not actually changing like a lot. At least during the season, they're seeing that. That's probably why they ruled that out. Yeah, they did have like a sea level change hypothesis, which they ruled out.
Okay.
In the first set of papers. Yes.
Thank you very much.
That was a great talk. I guess I'm curious about the universality, if you will, of the lack of wave energy in all of these lakes. It seems hard if we do have, say, snowfall happening, that we don't therefore have weather, and it wouldn't, in some times, in some observations, generate.
But you can also have the aerosols, which are going everywhere. Yeah.
And I guess that the same comment could be made about the islands if they're generated by mass wasting processes. Presumably, that would also generate some movement on the water that would generate a roughness.
Like,
I guess it kind of bothers me that it's always smooth, and like it seems like it should sometimes not be smooth with either of those mechanisms.
That's a good question, because actually I didn't say this, but we did only observe a few times that the lake is not smooth. We did observe like their roughness sometimes.
Is there any correlation of those in the islands?
Well, the islands, the problem is like the radar cannot tell whether it's waves or floating solid, so it could be it's floating solid, but it's also causing the waves, which are both seeing amplified by the radar. Apparently, yeah, they look the same on the radar because it's just roughness and stuff. Yeah.
Great, thanks.
Oh my God. Oh, wow, you guys are good.
Like a good talk. So my question is related to the.
Wait, are you the person who wrote the smoothness breaker?
Right.
Oh. Yeah, he's the person I was talking about. I think I cited him.
If it's floating simple molecules, right? So the source of them might be wasting molecules coming from the islands or atmospheric precipitation.
Right.
Right. Is it looking at how the very distinct and small size of the Magic Island, does it not rule out atmospheric precipitation?
Yes, it does rule out. So first, atmospheric precipitation will produce particles that are too small. So typically they're as big only as maybe like, I don't know, like 3 millimeter. That's the maximum, you can get with like snowfall, like ice particles from microphysics model. So that's one reason we don't think it's contributing. The second reason is like it's just gonna be, well, if it's a cloud just dumping on the lakes, but I just don't think it's like very likely. Why is it next to that island, right? Right. So I feel like it must be related somehow to the island. Otherwise, it could just be in the middle of the lakes, right? So I think it's in that sense, I would probably guess it's more like geology related, like not from the atmosphere. That makes sense. And great paper, by the way.
Hi, really great talk. Thank you. So I think about glaciers all the time, and I'm curious about this glacier theory
Okay.
because I feel like in theory, if it is a big glacier calving event, there would be some like lake level like rise to an extent. So I'm wondering like, have people explored that in terms of like that displacement factor if this was like a big ice calving event?
That's a great question. We have not explored it, so maybe we should talk more.
Okay, cool.
Well, question to that. Thank you for your talk. It was awesome. You made some connections to snow on Earth and the porosity related to ice. And for glaciers on Earth, within like the upper hundreds of meters, that snow is condensing into ice, and
Right.
the porosity is getting much lower. And if it is like mass wasting, is a similar process occurring for these solids, and they're condensing, and then the porosity is kind of decreasing as a function of depth. And
Mhm.
I guess the spatial scale of what you were showing, I mean, the island is like tens of kilometers,
Tens of meters.
tens of meters
Meters.
across. Oh, okay.
Yeah.
So are there any
Like
changes?
the depths, kind of like the material amount. I think it's about like 10 meters, I think, from what I read. Not like kilometers. The size of the island is big, yes.
Right. Okay.
But not the depths. But that's a good question. And I think I actually looked up like porosity levels for like the snow that are floating on the surface.
Yeah.
It is lower than like fresh snow, but it's still like 50 to 60% actually.
Yeah.
Porous. But like with depths, I think there's the porosity is not like super low, not like 20 to 30, but like still like 50 to 60. That's what I found from the literature.
How deep are the lakes? Do we know?
The lakes are deep. They're like some of them like hundreds of meters.
Okay.
Yeah.
So when you talk about a mass wasting event, do you think that this is a big piece that is kind of breaking off and then floating away from the solid part, and not necessarily like flipping or moving in other ways?
Like, I guess just like I just imagine it being like something like an island, and then something just came off it somehow.
Okay.
I don't know how, but that's where you guys can feel my knowledge gap.
No, that's helpful. Thank you so much.
Yeah, but we should talk more about it. Thanks.
Tim, could you unmute for your question?
Yeah, can you hear me? Okay. Cool. It's a great talk. That was super interesting. My question sort of follows up a little bit, I think, on Benjamin's question he was just asking. Have you in sort of mass wasting or glacial calving hypothesis, you have to have the mass balance, so that stuff came from somewhere, right? And so have you done any change detection elsewhere around the coastline? And I seem to recall that was one of the reasons, going back to I think Alice's question of like why they ruled out lake level change, is because there's no major changes in the coastline, which you would expect for lake level change. And so like, is there any indication of where this stuff came from if it is a mass wasting event?
I guess like it would be like from that island that's close by. And I don't know, like they definitely talk about if the island is removed. Again, this is not my area of expertise, so I'm trying to remember what the paper was trying to talk about. But they were saying if you remove like a massive, like enough part to form the island, at least that island would not be changing. But I don't think they talk about whether like the levels of the lake is gonna change. But I said, so that's thing I could look into. So that seems interesting. And it seems like you guys know way more about like glacier calving and mass wasting than I do. So that's very helpful. Yeah. Yeah, that's a good question, but I need to think about it. But maybe we should talk more.
Okay, speaking of talking more, we're after 11:30, so I'd like to thank Xinting one more time, and then also let everyone know that Eric Height's going to arrange lunch. So the plan is to meet in the lobby at noon. So thanks
Okay.
very much.
Thank you.